In this module, we will introduce the thermodynamic treatment of chemical equilibrium involving pure substances. When we talk about chemical equilibrium, we mean equilibrium in a thermodynamic system where a chemical reaction involving the transformation of reactants into products takes place. In this discussion, we will assume two key conditions. The reaction is happening at a constant temperature denoted as T. The system is maintained at constant external pressure represented by P. This means that the total pressure inside the system, even if there are multiple gases present, is always equal to the preset external pressure. The progress of every chemical reaction can be described by the quantity named extent of reaction Xi. No matter how many reaction participants are involved in the reaction, the extent of reaction is the only independent variable per reaction. Each substance involved in the reaction can be represented by an index, which we will denote as I. These substances, whether they are reactants or products, have associated stoichiometric numbers μI. The stoichiometric number essentially tells us about the proportion of each substance in the balanced chemical equation. At any point during the reaction, the current amount of any substance I can be calculated as its initial amount Ni0 plus the product of its stoichiometric number μI and the extent of reaction Xi. For any process at constant temperature and pressure, the direction of spontaneous change is the one towards lower values of the Gibbs energy G. In this module, we will apply this principle to the spontaneity of chemical reactions. Under conditions of constant temperature and pressure, reactions spontaneously proceed in a direction that reduces the system's Gibbs energy. The reaction will continue until the Gibbs energy reaches a minimum, indicating a state of chemical equilibrium where there is no drive for further change. Note that this spontaneity, dictated by thermodynamics, can be inhibited by kinetic factors. To determine the equilibrium composition for the reaction mixture, we analyze how the Gibbs energy changes with the reaction progress and identify the composition that corresponds to minimum G. Let us look at the total Gibbs energy of the reaction mixture as a function of the extent of reaction. This function is the sum of the product of the chemical potential and the amount of substance across all reaction participants. However, instead of directly analyzing the total Gibbs energy, we focus on its derivative with respect to the extent of reaction. The differential of Gibbs energy is equal to the sum of chemical potentials multiplied by an infinitesimal change in the amount of substance of the corresponding reaction participant. These changes are equal to the product of their stoichiometric number μI and the infinitesimal change in the extent of reaction. The derivative of the total Gibbs energy of the system with respect to the extent of reaction is known as the reaction Gibbs energy delta Rg. It is given by the sum of the product of the stoichiometric number and of chemical potential at the current composition of the reaction mixture across all reaction participants. Graphically, it corresponds to the slope of the plot of Gibbs energy against the extent of reaction. Chemical potentials vary with the composition of the reaction mixture, and the reaction Gibbs energy changes as the reaction proceeds. The spontaneous direction of reaction lies in the direction of decreasing G, and the sign of the reaction Gibbs energy indicates the spontaneous direction. If the reaction Gibbs energy is negative, the reaction spontaneously proceeds forwards. if it is positive, the reverse reaction is favored. At equilibrium, the reaction Gibbs energy equals 0. Hence, to find the equilibrium composition, we identify the point where this condition holds true. In our discussion of chemical equilibrium, we will focus on two idealized types of reaction participants. The chemical potential of pure solids or liquids can be assumed to be equal to the standard chemical potential at the given temperature. For ideal gases, the chemical potential is influenced by temperature and own partial pressure, as we had discussed before. We will denote ideal gases among the reaction participants with the index K. Now, the reaction Gibbs energy is equal to the sum of chemical potentials, each multiplied by the respective stoichiometric number. It can be represented as a sum of two parts. The first part is the summation of the standard chemical potentials for all substances multiplied by their stoichiometric numbers. It depends solely on temperature. The second part considers the effect of partial pressures of the ideal gas reaction participants. That first part is known as the standard reaction Gibbs energy, delta RG standard. It can be calculated as the standard reaction enthalpy minus temperature times the standard reaction entropy. These parameters can be in turn calculated from the standard enthalpy of formation and the standard molar entropy of reaction participants. Starting from the expression for the reaction Gibbs energy, we notice that the term involving the logarithm of the partial pressures can be reformulated. Instead of summing up individual logarithms multiplied by stoichiometric numbers, we can express this as a single logarithm. Specifically, it's the logarithm of the product of each partial pressure divided by the standard pressure, each raised to the power of the stoichiometric number. This composite term is what we refer to as the reaction quotient of pressures, denoted as QP. Now, let's break this down. Within QP, each ratio is a pressure divided by a standard pressure, essentially giving us a dimensionless quantity. Thus, it's critical to understand that the reaction quotient is dimensionless and unitless. When presenting a simplified version of the reaction quotient equation, the standard pressure is often left out. It implies that we are using numerical values of the pressures expressed in bar. A common pitfall is to use an equation of this type with numerical values of pressure expressed in pascals. This error leads to incorrect numerical results. The equation presented here shows that the current reaction Gibbs energy is the sum of the standard reaction Gibbs energy and the product of RT and the logarithm of the reaction quotient QP. While this equation is true for any point in a reaction, what interests us most is when equilibrium is reached. At equilibrium, the reaction Gibbs energy becomes zero. This leads us to the next equation where we equate the same expression to zero. Here, the reaction quotient at this point is denoted as Kp, the equilibrium constant. Essentially, Kp signifies the value of Qp when the chemical reaction is at equilibrium. Both the reaction quotient and the equilibrium constant are dimensionless quantities. From this relationship, we derive an equation that provides a direct way to compute Kp. It expresses Kp as an exponential function of the negative ratio of the standard reaction Gibbs energy to RT. It shows that the equilibrium constant, Kp, depends solely on temperature and can be derived from the standard reaction Gibbs energy. This equation is fundamental for chemical equilibria. With it, we can determine the equilibrium constant for any reaction using standard thermodynamic data. This allows us to predict the equilibrium composition of any reaction mixture, which is a crucial aspect for anyone working with chemical substances.